My name is John Broadwell, and I'm the creator of the open source Serial Wombat project. Today, we're going to give a demonstration in how to use the Serial Wombat along with your Arduino to debounce button inputs. The Serial Wombat is capable of debouncing inputs, as well as keeping track of how long each button is pushed and how many times it's been pushed, without additional supervision from the Arduino. That way, instead of worrying about whether the button is up or down at any given time, or trying to debounce it, or make sure that you don't miss a button push, your Sketch can do other things. The Serial Wombat will keep track of all the button transitions, and you only need to ask it periodically, has anything interesting happened? Let's take a look at the Sketch that we'll be looking at today. In our first example, we have two buttons, a green one and a red one. They are tied to ground on one side and tied to the Serial Wombat on the other. The Serial Wombat has optionally enabled pull-up resistors, so no additional hardware is required if you simply ground one side of your button. Additionally, the Serial Wombat internally handles logic inversion. That way, even though a pushed button pulls the voltage level low, the Serial Wombat will represent a pushed button as a true value to the Arduino. The Serial Wombat 6A and 6B can handle up to 4 separate buttons on 4 different pins. Let's take a look at the Sketch that we'll be showing in our example today. We declare a Serial Wombat. We declare 2 debounced inputs that will be on that Wombat. We initialize our I2C bus, making sure that we use the I2C address that corresponds to the Serial Wombat that we have on our breadboard. Our red button and green button we need to call begin. Those are the ones we declared up here. Pin 0 and pin 1 for red and green. We will enable the serial terminal so that we can send data out to be examined outside. We've got a function called clear terminal that, when used with PuTTY or TeraTerm or other capable terminal, will clear the screen so that all of our numbers appear in the upper left-hand corner. Note that this doesn't work on the standard terminal that's included with Arduino. We have a variable green transitions and a variable red transitions that'll keep track of how many times the button has changed state as reported by the Serial Wombat. In our loop, we'll clear the terminal, we'll read the number of red button transitions and add it to the variable. We'll read the number of green button transitions and add it to its variable. Then we'll print out the transitions and also how long the button, both the green and the red button, have been pressed. Then we'll delay for 50 milliseconds and do it all again. Let's upload this Sketch and watch it run. So here we can see we're ready to go. We push a button and we get a transition on red. We push the green, we get a transition on green. If we hold down the green, we can see we get one transition as the button goes down, and it starts counting how long the button's been held. When we let it up, the transition time goes back to 0, the transition count increments. So I can go back and forth, pushing my buttons. And it's as easy as that. Now let's take a look at another slightly more complicated example that allows us to control the rotation speed of a continuous rotation servo. The green button will make it accelerate counterclockwise. The red button will make it accelerate clockwise. The blue button will make it stop. We've attached the continuous rotation servo to Serial Wombat pin number 2. Remember that on the Serial Wombat 4B, pins 1, 2, and 3 are input or output capable. Pin 0 is input only. We've attached our red switch to Wombat pin 0. We've attached our green switch to Wombat pin 1. We've attached the servo to Wombat pin 2, and we've attached the blue button to Wombat pin 3. The servo is being driven from a 5-volt external power supply. I always recommend not driving inductive loads directly from your digital electronics. Let's take a look at our Sketch for the second example. We declare a Serial Wombat. We declare a Serial Wombat debounced input for the blue button, for the red button, and for the green button. Each of those are passed the Serial Wombat as a parameter. For the red and green buttons, we're going to want to be able to hold those and have them move the servo. In order to do that, we'll instantiate a Serial Wombat button counter for the red and a Serial Wombat button counter for the green. Note that we pass them the address of the red button that we declared as a debounced input. The Serial Wombat button counter is a class that runs on top of the lower level debounced input. My C++ skills are not as strong as they are in C or C#, and I was not able to figure out how to make this function take a reference rather than a pointer. If anybody wants to take a look at my library and give me some pointers on how I can make this work with a reference rather than a pointer, you'll have my gratitude. We're also going to declare a Serial Wombat Servo on the Serial Wombat. That'll be our output device. We're going to declare a long int, and note that the variable that we use with Serial Wombat button counter must be a long int. Not an int, not a char, not a uint8, not an unsigned long. It must be a long, or a long int. We'll declare it and initialize it to 90. The servo position range can go from 0 to 180. At 0, it will spin rapidly in one direction. At 180, it'll spin rapidly in the other direction. At 90, it should be at a full stop. In our setup code, we'll initialize the I2C bus. Then we'll initialize the Serial Wombat, handing it the I2C bus and the I2C address that we're going to be using. As before, we'll call begin on each of our buttons while handing them the pin on the Serial Wombat that they're using. When we do a begin on our counter, we will hand it the address of the variable that we want it to change. We will say we want you to increment one count every 500 milliseconds for up to 2000 milliseconds, after which we go into medium mode. In medium speed mode, we increment by 5 counts every 250 milliseconds, up to 5 seconds. Note that this is relative to the start of the button push. So this would be the period from here to here is 3000 milliseconds, 3 seconds. After 5 seconds of button push, we go into fast mode, at which point we increment by 10 counts every 100 milliseconds. We're going to set a low and a high limit for our button counter. By default, the button counters will let you run all the way to int min and int max, which is, negative 2 billion and change up to 2 billion and change. Well, we don't want that. For our servo, we have a range of 0 to 180, so we're going to set these limits. For the green counter, we're going to point to the same variable. We want the red button to make the variable go up. We want the green button to make this variable go down. So all of the parameters look exactly the same as they did with red, except our numbers are negative, because we want to decrement, not increment the variable. Other than that, they'll look the same. Again, we don't want the green counter to exceed those limits, so we set a 0 and a 180. We're going to attach the servo to pin 2, and we're going to tell it to reverse direction, because it turns out that for this example, it works better for me if it spins clockwise when I push the red button. It looks more intuitive. And we're going to begin the serial again so that we can show the position of the servo. Our loop becomes really, really simple. You tell the red counter to update. You tell the green counter to update. It's cognizant of how long it's been since the last time it was pushed, each time that it queries the Serial Wombat. So we could make this delay down here at the bottom 50, 100. We could even make it a random value between 1 and 250 that changed every single time. That's really actually quite useful, because if you have other blocking functions in your Arduino Sketch, the rate at which update gets called can be inconsistent. This is one of the challenges for beginners when they want to create a slewing button function like what we're creating. Finally, the blue button, which doesn't have an associated counter, we're just going to do a simple digital read on it. If the button reads true, then we'll reset our servo position back to 90. We'll write our servo position out to the servo, And we'll also dump it to the screen so that we can take a look and see what happens. Now let's upload our sketch, actually start pushing some buttons and see what happens. Here we see our circuit. If I hold down the left button, we'll see our 90 start to decrement, then decrement faster, then decrement faster. There's a significant dead zone on our servo, so it doesn't immediately start turning just because we drop below 90. If we push it farther, we'll see the servo accelerate as we go down to 0. If we hold the red button, it'll increment the angle reading being sent to the servo. It'll slow down, go into the dead zone, then change directions. If we push the blue button, it immediately sets the value to 90 and it stops. As you can see, once we get through this initialization, we get into our main loop, we get a lot of functionality out of 1, 2, 3, 4, 5, 6 lines of code. And additionally, this code will continue to run well regardless of whether I put 5, 50, 100, 250, or even generate a random number each time through here to change up our delay states. This is really useful because sometimes that's what your sketches actually look like when they are off doing other things or waiting for other user input. As long as your Serial Wombat is running, even if you're not paying attention to the buttons at a given moment, it is. If you have any questions about how to use the debounced input function of the Serial Wombat, please leave them in the comments below. Or, if you successfully use the debounced input function in a project, please leave me a note. Let me know what you're up to if you have any suggestions for future improvements. This has been John Broadwell, the creator of the Serial Wombat. The Serial Wombat open source project was created by Broadwell Consulting Incorporated. Broadwell Consulting Incorporated provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting. Support requests for Serial Wombat should be sent to help@serialwombat.com and will be answered on an as-available basis. Questions sent to John at Broadwell Consulting about the Serial Wombat will not be returned.